Hi, this is Kenny Lee, and I want to talk a little bit about light and color today. And so, to start things off, is a little bit of history about light. First of all, the Greeks had a pretty interesting view of light, and the way they saw it is, let's say, here's my person, there's their eyes, and they're going to look at something. The way they thought your vision worked is these little streamers shot from your eyes, and when they hit something, well, you saw it. That's why you only saw things that you looked at. You didn't see things that you didn't look at. Although we know that doesn't work, that we really know that light hits the object, reflects off, and then goes into our eyes, and that's how we see it. That was how they thought for a long time, is that these little streamers shot from your eyes. When they hit something, you saw it. Well, and that still pertains today. If you look at any of the like Superman or any people like that, that you see all the time that these X-ray beams shoot from their eyes or heat vision shoots from their eyes or something like that. And so that's basically where you got that idea from. Now, fast forward quite a bit, and we get to a couple guys that argued about light a lot, Newton and Huygens. And what happened was Newton believed that light was a particle. It was like a little BB almost that would hit and bounce off things and reflect off. And that's how light worked. And he had all types of different examples of it. One was like your shadow. If you stand out in the sun and you look at your shadow has very hard edges to it. It's very crisp. It wasn't blurry. If it was a wave, it should be blurry, but a particle should be crisp. And he would have all kinds of examples that show that light behaved like a particle. And all the people that followed his idea added to those listed demonstrations. Huygens, on the other hand, said light was a wave and that light could actually bend around corners. It actually had these other properties that he could use. And so he said light was more of a wave. And he would, again, have all kinds of demonstrations, and the people that thought like he did would add to those demonstrations to show that light behaved like a wave. And this argument literally went on for a century or so. Well, actually, several centuries, until Einstein settled the argument. He said that light was both a particle and a wave, and we call that the dual nature of light, that it's both a wave and a particle. If you set up your lab or demonstration where you need light to behave like a particle, well, it behaves like a particle. If we needed to set up our stuff where we're using light as a wave, well, it behaves like a wave. It does kind of whatever it needs to. And we call that piece of light, we call it a photon. Photon is what we call like a wave packet, that from up close, it looks like a wave, but far away, it will look more like a particle. And that's sort of the dual nature of light. Depending on how we're using it in our demonstration is how it essentially works. One thing that we figured out about light is the speed of light. The speed of light, we give it a special letter, we call it lowercase c, is equal to 3 times 10 to the 8th meters per second. Now, how do we find something that goes that fast? You can't just time that with a stopwatch. You can't have somebody say go and time that, although we'll find out that somebody actually tried that. Let me give you a little bit of history on this one too. The first person that I know of that tried to figure out the speed of light was Galileo. And what Galileo did was he got on top of a hill and he had a lantern. And he sent one of his students out to another hill with that student also had a lantern. And these lanterns had little openings on, so they could open it up, send out a beam of light, close it, shut it off. So the equivalent of a flashlight, essentially. And Galileo would open up his, send out a beam of light, his student would see it, open up his lantern, send a beam of light back to Galileo, and Galileo essentially timed it with his pulse or some other device. And he got a distance and a time, so he can figure out, I can find the velocity. And so he did that and got a number. And then to check his number, he did the same experiment again, but this time sent his student out to a hill that's even further away. And when they did the exact same experiment over again, they realized that he got essentially the same time. And that was weird to him. So he thought, well, either light exists everywhere as soon as it comes into existence, or he said that simply my experiment is not good enough to determine the speed of light. And he decided that it's probably his experiment. So he kind of gave that up and went into other things that eventually got him in trouble with the Catholic Church. But another guy that kind of was helped by Galileo, because this guy was named Romier. R-O-E-M-E-R. And Galileo had discovered that Jupiter had moons going around it, which was part of his problem with the Catholic Church. And what Romier was doing was studying one of Jupiter's moons, particularly the moon Io. Okay, there it is, Io. And okay, let's say we've got obviously this is not drawn to scale, that's Jupiter. Over here we have the sun. And let's say this is Earth's orbit, which is much more circular than what I just drew. And let's say when the Earth is over here, Romier was studying Io, and he figured out that in a certain amount of time, Io went around Jupiter so many times. So he can make a prediction about how long it took Io to go from here around back to that same location. And so by that, determine how long Io would actually stay hidden behind Jupiter. When the Earth was over on this side, it was coming out a little bit quicker. But when the Earth was over here, the moon was coming out much later. And he couldn't figure out why that on this side, the time it took Io to go around seemed different than on the other side. Well, it turned out that Io wasn't the problem. It was actually the distance from one side of Earth's orbit to the other side of Earth's orbit. Although Romier didn't know this distance, so he couldn't really come up with that calculation, it gave people the idea. One was Huygens. He determined that if you kind of knew that distance, which we don't think he did, you might be able to figure out that it was the difference in that distance between where light had to travel to here versus where light had to travel to here that was the problem. So we still didn't know the speed of light, but we had a good idea about what it should be from measurements later on where we kind of did know this distance. And so Michaelson actually figured out. Michaelson was the first American to win the Nobel Prize, and he won it in physics for this experiment. He had a light source, and he had this mirror. And this mirror was 8-sided, so it looked like a traffic sign with a mirror on each edge. So there's a mirror here, 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 all the way around. And he had it on top of a turntable that he could spin. And he could control the amount of spin because it was connected to an electric motor, so he can adjust it to go spin faster or slower. But with everything sitting still, he had his light source, and he shot a beam of light that hit this mirror, reflected off, and bounced off to a mirror that he had on a side of a mountain about 35 kilometers away. So pretty good distance. It would reflect off that mirror, come back, hit this mirror here, and if you're standing in just the right position, that's an eye. Standing in just the right position, you would see the beam of light. It would flash into your eye. But when you started spinning it, if it didn't exactly make 1/8 of a turn, let's say it only made part of that, this side only went from here to here, then that beam of light coming back would hit this side and reflect off this way, and you wouldn't see it. If it spun too quickly, this side would over-rotate, it would hit and reflect down this direction, and again, you wouldn't see it. The only time you would see it if the mirror took exactly 1/8 of a turn during that pulse. In that case, he could get the time from measuring the speed of the mirror, speed of its rotation, and he knew the distance because he set up the mirror 35 kilometers away, so it's 35 kilometers out, 35 kilometers back. He could use that distance with the time, and actually figure out the speed of light, which you got what we round off to be 3 times 10 to the 8th meters per second. And he won the Nobel Prize for that. So that's our standard value of the speed of light. And we use it so often, we've got a special letter C. And that is the C that's in the most famous equation ever, E equals mc squared, where C is 3 times 10 to the 8th squared. Okay, so that's how we discovered the speed of light. What else do we need to know? We now know that it's both a particle and a wave. We call it a photon. That's the dual nature of light. The speed of light, 3 times 10 to the 8th. Light can interact with matter a couple different ways. Matter can be transparent, translucent, or opaque. And what's the difference? Well, transparent, well, makes sense. You can see through it. Opaque means you can't. Translucent means you kind of can see through it. So the definitions go something like this. Transparent would be like a regular window or the glass in the windshield of your car. You can see through it, doesn't distort things, fine. Opaque means light cannot travel through it. So it would be like a wall or tabletop or something where light simply can't pass through. Translucent would be something on the order of like maybe windows at like a church where they're textured, or maybe some glass dividers where you don't want to see through, but you also want light in. And so it's textured where you can tell that there may be a person out there, but you can't tell who that person is. Or you can tell that there's a tree outside, but you can't really get any details from it. So everything's kind of blurry, out of focus. That's translucent. Now, different wavelengths are transparent, translucent, or opaque to different wavelengths of light. For example, the glass of your windshield of your car is transparent to visible light, but it's opaque to ultraviolet light. So no matter how much you sit inside your car on a sunny day, if you got the windows rolled up, you're not going to get a tan. You may get hot, you may turn red because of the heat, but you're not going to get a tan. That's because the ultraviolet light that gives you that tan gets blocked by that glass. And so that glass is opaque to ultraviolet light. But let's say the wall of your house, which is opaque to visible light, is transparent to radio waves. Radio waves pass through your house very easily. That's why your cell phone works in your house, or why maybe you can get TV reception or radio reception. But for visible light, it completely stops it. So different materials are either transparent, translucent, or opaque to different wavelengths in the electromagnetic spectrum.